Having established the ground rules about imine formation, we can now look at the detailed mechanism. So recall that an imine is formed when a primary amine reacts with an aldehyde or ketone. So the first step in the mechanism is going to be nucleophilic attack of the neutral amine on the neutral carbonyl carbon. So this leaves us with an intermediate in which we have a positive charge on nitrogen and a negative charge on oxygen. This is the sort of intermediate that we said was not possible with oxygen nucleophiles. It's still not a great intermediate. This step is most definitely going to be uphill, this step. But this intermediate is okay because the protonated nitrogen is fundamentally not a strong acid. It's not the fact that we have a plus and minus charge in the same intermediate that's a problem with the oxygen nucleophile. It's the fact that you have a strongly acidic hydrogen and a strong base present in the same intermediate. In this case, we do have a strongly basic oxygen, but we do not have a strong acid present. The acid is weak. However, a strong base plus a weak acid is going to result in proton transfer. So in this case, it's going to be an intramolecular proton transfer from the oxygen. The electrons come from the oxygen, pick up the hydrogen, the electrons in the NH bond go on to the nitrogen, and the effect is to give us a neutral carbanolamine. Now, to move forward from this point and get us to the imine, we have to protonate the oxygen in order to make it a good leaving group. Okay, so the mechanics of that are going to be the same as any other proton transfer. The electrons on the oxygen go pick up a proton. So now the question is, what is the source of this proton? And as you can see, the source of the proton is CH3NH3+. Okay, so what we hopefully established in the previous video is that the reaction is carried out at a pH approximately between 4 and 6. Those are the ideal pH ranges for this reaction. So at the reaction pH, CH3NH2, the basic form, and CH3NH3+, the acidic form, are both present. In fact, there will probably be more CH3NH3+ than neutral CH3NH2 present at this pH. This, the CH3NH3+, is the acid used to protonate because H3O+, which is what people like to sometimes use as an acid, is not present in this reaction. We will generate a molecule of water later on in this mechanism, but as you can see, as you will see, we will want to get rid of that water, not have it around to get protonated, and the pH is not low enough to have any significant concentration of H3O+ around anyway. Okay, so arrow from the oxygen of the alcohol to the hydrogen of the acid, and then another arrow breaking the NH bond and putting those electrons onto the nitrogen. So this leaves us now with an oxygen that's forming 3 bonds, 2 of them to hydrogen, and having a positive charge. And as you can see, it is poised in the next step, which we will get to in a moment, to expel water as a leaving group. But before we get there, I want to go over one more point with you, and that is the nitrogen in this second intermediate is actually the most basic site. If you were going to protonate something, if you have the choice of protonating the oxygen versus protonating the nitrogen is going to want to be protonated preferentially to the oxygen. Protonation of the nitrogen can occur, and it does occur, but the problem is protonating it there does not take us forward. Protonating the nitrogen is along the path that will take us back to starting materials, as you'll see in a subsequent video when we do the reverse mechanism of this reaction. Protonating on oxygen happens only a small percentage of the time, but it only takes a small percentage of the time because this step can be pushed in the direction that it needs to go in by a more favorable step later on in the mechanism. So keep in mind this is not a particularly favorable step, but it still happens to enough of an extent for it to be a reasonable step in the mechanism. And secondly, protonating on oxygen is the only way we can actually move forward and get to product from this point. Okay, so as we said, we had set up to expel water as a leaving group, and then in step 4 we actually do that. We expel the water as a leaving group. Break the bond, you need one arrow. Electrons go from the bond to the oxygen, the more electronegative element, and that leaves us behind a carbocation. Now this carbocation is an azocarbocation. You have a plus charge on a carbon next to a nitrogen, and another name for it is that it is called an iminium ion. Okay, so it is a resonance stabilized carbocation where we can have electrons from the lone pair on nitrogen come down and form a carbon-nitrogen double bond to get rid of carbon's electron deficiency problem and instead put the positive charge on nitrogen. This second resonance structure is a favorable resonance structure because in it all atoms are obeying the octet rule. And in this case, it's even more stable than the oxocarbocation because nitrogen is happier with a positive charge than oxygen is. Nitrogen is less electronegative than oxygen is. Which brings us to step 5. We now have a structure with a positive charge on nitrogen, and this is weakly acidic, but it can still be deprotonated using an equivalent of the strongest base we have around right now, which is CH3NH2, to generate the neutral imine, which is the product that we want to get. Okay, so now we have to consider the equilibrium for this reaction. So as I have said, all of these steps are reversible. They are all drawn with equilibrium arrows. Some of them are unfavorable in the forward direction. So what actually drives this reaction to completion is, first of all, that we generally do it with an excess of the amine present, and secondly, we remove water. Okay, remember Le Chatelier's principle? If you can remove one of the byproducts, and water is a pretty easy byproduct to remove, as long as you do the reaction in the presence of a drying agent, either magnesium sulfate or molecular sieves, you remove the water that is expelled in step 4. In order for the reaction to go backwards, you need water to be introduced into an intermediate. You need to essentially do the reverse of step 4. If there's no water to do that, if the water is removed as soon as it is formed, that step 4 then essentially becomes an irreversible step, which therefore drives step 3. Okay, so step 3 is most uphill energetically, but the loss of water drives it. So there you have it, 5 steps to get from an aldehyde plus a primary amine to an imine. Now, in the next video, we will look at the reverse of this mechanism. Remember, I say I want you to know these mechanisms forwards and backwards. The reverse of this mechanism then is the hydrolysis of an imine to give you a primary amine and an aldehyde or ketone.